let's talk about how we can use this amazing resource in our calculators here. All right, so first things first. Okay, so let's go. Yeah, this is looks different, doesn't it? That's what we want. So this is the.
Our screen looking like that right
No,
now? Okay.
no, yours. I mean, it'll look similar.
Wait, do you have to buy these, like a calculator or whatever, when you have them back? Do you
Yeah.
buy them?
I buy them. There is a free one you can get.
For like Android and stuff.
Well, I think it works on. Actually, there is an emulator for like an iPhone or an Android that is, I believe, it's even free, and it's pretty slick. I mean, it has all the functionality of the graphing calculator. It's amazing.
It's funny, a couple years ago, like there was this app that like everybody like at my old school was like really excited about. It was supposed to solve math problems for you and like and show you what my teacher tried doing it and it didn't work.
No, it works.
It didn't work for his.
That's how I got
Is that how you
on
do
his algebra
it?
2. No, this is pretty like I haven't used it since like sophomore year, but on his algebra 2, that's all I use because Mrs. Bidwart is a really good teacher.
Oh,
He was done with the class by the first week. Honestly, he sounds really great.
I was done with it because I was in that class.
I was in that class for half a year.
Psych, wasn't even here. I don't know what that was. Don't ask that.
You got us.
Okay, I'm not seeing. How do I get rid of that on here?
What do you
Well, I just want to get rid of this, and it's a little different than it was last year. So hide screen captures right there, I think. No. How do I do this?
What, you're trying to get rid of that?
Yeah, I just want to get rid of this little sidebar here.
Don't you need the sidebar to see?
Well, we will shortly, so I'll leave it. But I'd just like to know, what's this right here?
Hey,
Well, why would it let you move because that's like the screen, you need the screen of
Yeah, you need
calculator,
the
so
screen.
why would it let you move it? Or do you just want
Oh,
it
yeah, you're right. So I just want it to be, why do I want it on the side? I do want the screen. Can I not put it up above?
Wait, on that one button you click down the bottom corner.
Does that do it?
It had like a calculator right next to it. No, the bottom one, pull that toolbar up.
Oh, right there.
That is.
Oh, okay, that's something different.
Wait, go back to view.
Go back to view?
Yes. Go calculator faceplate.
Oh, emulator position, actually.
Oh.
Left, right,
That's just the same thing.
toolbar position.
Yeah.
Okay, I think I know what it is. I bet I know what I have to do. I think if I go like this. Oh man, so now.
I don't think it'll move.
Well, maybe that's.
Calculator green to the left.
There we go. Nice. Okay. Bingo. There it is. Good work. Okay. So we want to do. We're trying to find. Oh, I recorded that whole thing. Sorry. Well, I meant to pause that. I'm not very good at controlling my recording, so you're going to get lots of that kind of crap in there probably. So number 10, we want to complete this table, right? We're trying to find the limit of cosine x minus 1 over x as x approaches 0. Okay, well, one thing we want to get straight here is we're going to use a calculator for this. What is the implied unit for my angles that I'm going to use here? Radians or degrees? Radians. Okay, so we want to make sure you're using calculators. This is far and away the most common mistake people make when they're doing any kind of trig stuff on a calculator is they don't set the mode to radians. Okay, this is on the new calculators, the default is radians, which is good. I think we're good. Okay. Okay. So this is done with a table, right? It looks like the table has values that are moving selectively closer to 0, okay? A couple ways we could do this on our calculators. We can be really tricky with this. We could say, one thing we could do is we could actually build a table. Okay, so we can go, notice up here, I can go second F5 is table. Actually, I'm gonna do table set. Second F2 is table set, okay? So we're gonna, how about if we start at negative 0.1. And delta table means we're gonna move in what kind of incremental steps. How about if we just move in increments of 0.01, okay, 1/100th. Okay, enter, we're good. So now let's go up to, we have to actually set up the function that's in the table. So to do that, we go to y equals, and then we're gonna use y1. All right, so we just need to put this into there, right? Now there are some shortcuts here that if you're not aware of, I'll show you. If you hit alpha F1, it gives you a shortcut menu to fraction templates if you want to use fraction templates. You don't have to, we could just use a string and put parentheses, but let's go ahead and do this. So there's our fraction template. On the top, we want cosine x minus 1 over x. Okay, enter. Make sense?
My calculator messed up.
Uh-oh, what did it do?
In the graphic part, it won't let me bring in fractions. It's usually we
You know what it is? Yeah, okay, I know what it is. I need to update this for you, or you can update it. If you go to second memory and hit about, it'll tell you what, oh no, that should be fine, 2.55, that should work.
Second y equals to get,
Oh, okay, you're in inequality,
Oh.
Yeah.
Okay.
so you wanna get out of that. So you're in an app, so it won't work there. So you just go apps, and then you go down to, we'll hit alpha I to skip down to the i's, go into inequality and quit. Okay, now it'll work. Yeah, now you're fine. So now if you go alpha F1, there you go. Okay.
Thank you.
Mhm.
I've never had issue with it. It's like reading or whatever.
So that's.
Rookie. All right, so now if we go up to second table, look what we get. Okay, it gives us the corresponding values for y, and we can just space down the table. Notice it gives us an error at 0, but what's y seem to be approaching, right? Right, seems to be approaching 0, doesn't it? Okay. Another way we could do this, if we want to just maybe fill in the table in the book, or maybe just write a table out, and we don't want to be linear like this. Notice that this is sort of logarithmic, where the x values are diminishing by factors of 10, right, as we move closer. Another trick on the calculator we could do is we could set up this expression here and input values of x. Okay, what I mean by that is we can store a value for x, like let's store, for example, the value negative 0.1. How do we do that? Negative 0.1, we just hit store x, okay? And now that's in there for x, if I hit enter. Okay, so anytime I hit x, it is now giving me back the stored value of negative 0.1. So let's just build this expression and evaluate it by grabbing it and changing the value of x. It's a really efficient way to evaluate functions on these calculators. Does that make sense? Well, it will after we do it. So let's go to our template again, alpha F1. And so we're just going to build this expression, cosine of x minus 1 all divided by x okay, and we just hit enter. And that's the value of the function at negative 0.1, okay? So what do I do if I want to evaluate the function at negative 0.01?
You change the value of x.
Yeah.
That's wrong.
Good, so I just go negative 0.01, store x, enter to store it, and then I'll just go back up, grab that algebraic expression, and hit enter. There's the value, right? And I can do the same, see how that's working? I can do the same thing then, let's do one more. So if I do negative 0.001, store x, enter. Once again, just go up and re-grab that expression, right? Etc., etc. Okay. We could graph it. Another option, right? We could go up to graph. Now, I'll show you some tricks on graphing too. These calculators are excellent. They're extremely useful, but it really helps if you know what you're doing, if you can be efficient on it. I'm going to do this so we can see this a little better. Let's go y equals, we've already got this function in there, right? So let's set the domain.
Would you have to unstore the x value?
No, you don't. You never have to do that, because as soon as the calculator needs to use that x variable, it will. Okay. So we need to go up to window, right? We want to set the domain of the window here. What do you think we would probably choose for our domain based on that table?
Something really small.
Yeah,
0.0.
like negative 0.1 to positive 0.1, something like that. So x min negative 0.1, x max positive 0.1. What does the x SCL mean? Scale. So that's going to be where the hash marks are. I usually don't even mess with that, but if we wanted to, we could make the hash marks like every 0.1 or 0.01. 0.01, how about?
Wouldn't
So-
that- No, it'll jump the graph too, wouldn't it?
No, the scale won't, no. And what about the y's? We'd have to calculate it, but there's a trick. We don't want to have to figure out what the y's would be doing. Let's let the calculator do it. So we go zoom 0, which is zoom fit. If you scroll all the way down to 0, you see it's zoom fit. And you don't have to scroll, just literally hit zoom 0 every time. It will calculate the size of the window to match your function. And there it is, right? So on that interval, do you suppose that's a linear function? No. But on that interval, it appears to be pretty linear, doesn't it, on that very short interval? Okay. Pretty clearly, what is the value that it's approaching? 0. Okay. How do we evaluate points using the graph? Okay, there's a way to do this also. So we can go up, and I am recording this, good. So we can go up to second calc, and that's giving us, so second F4 gives us our bag of tricks for graphs. There's lots of stuff we can do. In this case, what we're trying to do is maybe find the value of the function, right? So we'll just hit 1 or enter and put in an x value, like negative 0.05, for example. And then it puts the cursor there, and it tells us the x and y value. There's a shortcut for that. It's easier, fewer keystrokes. You can just hit the trace button and then override that with a value. So if I say 0.05, it does the same thing. So trace, enter an x value, and hit enter, and it will also evaluate the function. Now, the x value you choose has to be on the window, though, I think. Pretty sure. Let's try it. Trace 1. Yeah, see, it won't do it. It's got to be on the window. So what if we hit trace 0? Oops, gotta go graph first. Trace 0. No y value, how come? There's a hole, yeah. And that's the only way to find the hole on a graph is it's not gonna show up, right? It'd be nice if they put like a little circle there. I've never seen any graphing technology that does that, but that would sure be cool.
TI-85.
There you go. There was a TI-85. Yeah, and it was terrible.
There's a guy 89 too.
TI-89 doesn't do it either. TI-89 is great. Honestly, I sort of kind of wish we used that in calculus a little bit, but I don't want you to go out. If you want to get one, I know how to use it, and I could show you, but it's not necessary. What it does that's really cool, it's actually harder to use for most things, but it includes a built-in computer algebra system. So it will do analytical work with symbolic algebra, which is pretty cool.
That's what the map is.
What's that?
This app that I have that's really fair and balanced does.
That does
You-
algebra.
Yeah, just you can. That's on his algebra too.
Yeah.
Yeah.
Yeah. Yeah, and so the 89 does that. I used to actually, back in the day in Binville, that was kind of the required calculator for calculus, but.
So, and now that calculator would be allowed like in SATs and stuff, right?
I don't know. I can't remember what the rules change all the time. I'm not sure.
But
to look. It
like,
might not be.
The average
84s
administrator
are.
probably wouldn't.
No, they would know.
They would know.
Yeah, they'd know. I mean, they check that stuff. Yeah, and I don't know for sure if it is or
Wait, why
not. It
did the
should be.
numbers go backwards for the calculator?
I don't know.
That's just-
I don't know. The 84 was actually around in like an earlier form, but it just had never really taken root yet, and then it just got improved.
So now they're just adding letters to the end.
I guess, yeah.
That way people feel comfortable saying.
There you go.
Or, but
There you go.
so bad.
Okay, so does that make sense? All that stuff?
The Apple version of calculators.
All right, so what next? Anything else? Other questions? Good for now? Okay. All right, so what I want to look at today, I want to look at, we talked about numerical and analytical ways of evaluating limits, but hopefully that offends your sense of, well, I don't know, of your sensibilities when it comes to math, because doesn't it just seem like there's some limitations to, to calculating limits in that way, right? I mean, what if the table is all over the place, right? There are certain situations where it might be hard to even do a table because maybe your limit involves other variables. Maybe it's not easy to graph. Maybe you're taking a conformal mapping of a Calabi-Yau, 7-dimensional Calabi-Yau space, and that's not going to work well, right? So you got to be able to do things analytically. We got to be able to use algebra and come up with a definite answer based on a rigorous algebraic approach. Get the right answer, not just an estimate. Okay, so Calabi-Yau, in string theory, it's a 7-dimensional space, subspace of.
Yeah, sorry.
Yeah.
Space,
How
yeah.
did you not know this grade?
I'm sorry.
Yeah, come on now, come on now.
I found out, yeah.
Okay, so let's take a look here.
So
Let's
what
take a
are
look
the
at
7 dimensions?
Oh, we'll get on this later. Don't get me off topic. I know what you're trying to do.
Wait, do we get to learn string theory?
No, we can talk a little bit about string
Just
theory.
Piece it together, and we'll eventually get it.
String theory is pretty advanced. There are literally like a handful of people in the world, and I'm not one of them, who understands in a comprehensive way the math of string theory. I mean, and a problem is that some of these guys are starting to get old, and so there's this big lobby in physics for them to sort of teach other people.
Wait, why
To
don't
be
they
that
teach
good.
other people?
Well, they do, but you want to talk about a weed out process. I mean, there's these guys that do string theory, the math of string theory, are ridiculous. I mean, their IQs would be just off the, 220 plus kind of IQs, and it's all focused on this, and you have to have that capacity to be able to keep all this stuff straight at this point. I mean, string theory is just a daunting mathematical.
What is string theory?
String theory is it's the leading candidate for a physical model that synthesizes the physics of gravity, of general relativity, and quantum mechanics. So it's kind of a theory, the leading candidate for theory of everything, a theory that would describe all of physics within a single mathematical model. And we'll talk more about it. I mean, but it's really cool.
It's
And there's
based,
some, but it's extremely complex.
it's essentially based off of everything being made out of microscopic understatement, but strings.
It is, yeah,
Yeah.
of one-dimensional strings, yeah, that are little, like literally little filaments of probably energy on the Planck scale, so the scale would be about as small, below a certain scale, the universe, mathematically we can subdivide the universe infinitely, right? But physically it turns out probably we can't. String theory and some other indicators seem to point to there being a bottom limit to size in the universe, about 10 to the minus 43 meters. Below that, the universe is no longer granular. You can't get smaller than that in our universe, which is a little strange, yeah.
What was the approach before string theory?
What's that?
What was the approach before string theory? Like, did they have a thought like making it out of?
Well, I mean, string theory goes back, actually, in its roots, string theory goes back a long.
Oh, so it's just always been string theory.
Well, no, I mean, it's fairly new, but I mean, the precursors of that were like supersymmetry, and there were some, well, we'll talk more about that
So
later. Yeah.
there's a string of incorrect string theories, if you will.
Uh-huh, okay. So how do we deal with stuff like when we're trying to evaluate limits analytically? Let's just take an example. What if we've got something like, okay. We'll just do something like that. So here's our function f of x equals x squared plus 1. Remind me real quick, what's a limit? When I say something like this, what am I saying?
Just say
Where
the
you
point is
anticipate to be when you're on C.
Say it again.
It's where you would anticipate the
Okay.
graph to be the best for C.
Good, okay, as x approaches c, ants walking from both sides along the function would agree that the function approaches a value of L, right? Doesn't matter what happens when you actually get there, but that's the value that they anticipate approaching. So let's take a function like this. What is the limit of this f of x as x approaches -1? Answer is 2. How'd you get that?
for x.
Okay, so we plugged it in for x. Okay, that's called direct evaluation or direct substitution. Why does it work?
Because that's the real
You're on
answer.
an easy
Okay.
equation.
Because that's the real answer, but there's a little more to it than that. That's the real answer, but that's also the value that the ants are approaching, right?
So is it possible to have a real answer that you can't just plug it in with the
Sure.
direct thing, but to where the ants wouldn't expect it, so to speak?
Yeah, we can do it right now. Well, we will in a second. Here's what I could do. I could just put a hole there and put that point, drag that point up there.
Okay.
Right.
Where did the holes come from? Just from like.
So holes are
When stars collapse. Create.
holes occur when mathematically you get holes in a function when the
Like the
It's-
denominator is x, and so there's a whole zero.
okay, but it has to be more than that. It's a location where in a rational function both the numerator and the denominator have a 0.
So how would you get a hole with that equation since there's nothing there? Right?
Well, it wouldn't be that
One.
specific equation, but that's just an example graphically.
It would be, right, so like, we looked at one yesterday that was real simple. We looked at x cubed over x, right? And because the top and the bottom both have zeros at x equals 0, that constitutes a whole. Okay, we'll get into that in much more detail. Compare that to what if only the bottom equaled 0? Like if I had something like x plus 2 over x. As x went to 0, the top would be 2 and the bottom would be 0. That's not a whole, that's an asymptote, vertical asymptote. But we'll talk a lot more about that later. But for now, let's go back here for a second to this idea. Whoops, to this idea. The answer we got was 2, and we got that by direct substitution, right? So, that's not drawn to scale, but you get the idea. The answer that was given to me was that's the value of the function. That alone is not significant. There's something else that has to go with that. It's the value of the function, but in this case, the ant will end up stepping where he anticipates stepping, because there's no funny business going on, right? There's no hole, there's no weirdness to that function. Does that make sense? So it's a pretty bizarre, convoluted way of looking at this, but it's the way you have to look at it. When we use direct substitution, we're using the actual value of the function to inform our prediction of where the ant would step. Does that make sense? Because he is going to step where he thinks he's going to step. The easiest way to find out where he thinks he's going to step is to look at where he actually will step, right? Does that make sense? Okay, that's different than the situation we looked at yesterday, which was something like this. We looked at a bunch of examples, but let's just say, let's pick this one, right? Or there's a hole there. So this is g of x equals x cubed over x, right? Direct evaluation doesn't work there, does it? If I try to take the limit at 0. What happens if I try to plug in 0? I get 0 over 0. That's indeterminate, right? That doesn't give us an answer. See what I'm saying? And so that's where it falls apart, because this time we can't rely on that simple strategy. This time we can't predict where the ant's going to be based on where he actually will be, because he's not going to be there. See what I'm saying? So how can you distinguish between the two? How do you know when you get an answer like this? When you get an answer. If I evaluate the limit and I get an answer, I'm done. Then that means that the function actually exists there, and so that's an easy way to predict where he thinks he's going to be.
So what about that scenario in which there's a hole in a real answer about the interval?
Okay, so that would be, so a situation like that is a little bit contrived and a little bit different. Then that would be kind of a graphical situation anyway, right? So if we have, what if we have something like this? What if we have something like that, right? Well then, where's he going to be? It's going to be based on the graph. He thinks he's going to be there, right? And so that's the answer to our limit.
But if there was like another graph, if there was a break in the graph, then there would be no limit.
Right, but that we already said that, right? Limits don't exist where there's a break in the graph.
So the answer to that
It's still the same.
Would be there. That's the limit.
still be there.
Yeah, because that's where he thinks he's going to go.
Okay, but what's the significance of the other one up higher?
Well, that's the actual value of the function.
How would you ever get that though?
Well, if we were to, let's say that's, I don't know, say that's 4, for example, and this is h of x, let's say. So h of -1 is equal to 4.
We had something like that yesterday, where it was like h equals 14, and then it's like x is between 7 and 4, and then like another one, and it had a graph like that.
Yeah, where there's some funny business like that. Yeah, so this is one where if the ant actually took that last step, he would find himself beamed up to that little point.
So that's like not part of the actual function, that would be like another.
Well, this would have to be defined as a piecewise function,
Okay.
right? Okay. So piecewise function is something like this.
We had one yesterday.
So a piecewise function would be something like if we have f of x, let's say it equals -1 when x is less than 0, it equals +1 when x is greater than 0, and it equals 0 when x equals 0.
Okay, I remember that one.
Remember that kind of stuff? Okay. Does everybody understand? If I put something like that up here, you know how to interpret that? Okay, so if I were to graph this thing, it would just look like, this, right? Does that make sense? Okay, good. All right, so then, try another one for me. Without a graph, see if you can find the limit of this function. What's the answer? -4. Right? How did we get it? Direct evaluation. It worked, right? Whenever you can directly evaluate a limit, do it. It's easy, right? That's what you want. The only time that this falls apart is if you get a different kind of an answer that's not a number, right? So for example, for now, we could say, I want to make sure I get this in an order that's going to make sense. Okay. Well, I'll do this now. So what if we do something like this? What if we do the limit of 3 minus x over x plus 2 as x approaches -2? What are we gonna get? We're gonna get 5 on the top, right? Over 0 on the bottom. Okay, that actually, in a way, is a problem that you're gonna like right now because we're done. You can't divide by 0, right? A number divided by 0 is forbidden. And so what do you think the answer is if we're trying to find a limit there? No limit, yeah. So that answer is no limit, done.
So how would it be on the graph?
That's gonna end up being a vertical asymptote.
Okay.
So we got two kinds of answers. We're gonna try to directly evaluate a limit, and if we get an answer, we're done, right? If we get a numerical answer, that's direct substitution work, and that's the limit. Easy to, done. If we try to evaluate a limit and we get a number divided by 0, we're done. The answer is no limit, and we did our work, right? When it gets a little more complicated is if we're gonna do a limit like this. So those are the first two kinds, and those are quick and easy. This is the kind that requires more work. If we're gonna take a limit of something like x squared minus 1 over x minus 1 as x approaches 1. Okay, what do we get if we attempt to directly evaluate that?
0.
Okay, we get 0 over 0, which is an indeterminate form. And so what that means for us is we gotta do more work. Okay, that is not a good answer. An indeterminate form means that we don't know what the answer is. It could be numerical. It could end up being, in rare cases, that there still is no limit, but we don't have an answer yet. We gotta keep going.
Indeterminate because both top and bottom equal 0? Or?
Yes.
Okay.
Yeah, because what is 0 divided by 0? We should know it. There isn't an answer to that.
We should ask Siri.
Just ask Siri.
Have you?
No, I never have.
You have?
No.
Yeah.
What does she say?
Oh, it's great.
Kind of curious.
What's 0? What's 0 divided by 0?
Imagine that you have 0 cookies and you split them evenly among 0 friends. How many cookies does each person get? See, it doesn't make sense. And Cookie Monster is sad that there are no cookies. And you are sad that you have no friends.
That's pretty clever. That's pretty good.
Yeah.
Siri's got a sense of humor after all. Okay. So that's our goal then, is we got to figure out an algebraic way of taking care of this situation. What happened? Well, there's a hole in the function there. And so direct evaluation failed because the function isn't defined there. Okay. All right, so any ideas what maybe we could do?
Factor it out.
Okay, yeah, we could. We've got to do some algebraic work. And what we're going to see here is that we're always going to end up canceling factors, top and bottom. Okay, that's always going to be the case. There's going to be, when we get this thing factored somehow, and in this case it's pretty easy. We'll see some other cases where it's a little more difficult. But when we get this thing factored, there's always going to be a factor on the top and a factor on the bottom that share a 0 of 1. And when those cancel, we eliminate the indeterminacy. Okay? So we're going to rewrite this. We're going to rewrite this as the limit of x minus 1 times, what's the top factor into?
Plus 1.
X plus 1. Good. Divided by x minus 1 as x approaches 1. Okay, so now look what we can do. We can cancel the offending factors, right? Those were the factors causing the hole. Okay? Our answer just ends up being equal to the limit of x plus 1. And as x approaches 1, what is that? 2. Okay, what did we just do here, though? How much time do we have?
2 minutes.
Oh, seriously, 2 minutes?
Yeah.
Gosh.
Okay. So
Okay, but no, hang on, so we got to finish it. Okay, so this is really important what we did here, though. This is really cool. So what we did is the blue function, our original function, call it f of x. Here's what it looks like. Okay, if I were to graph this, it is this. It is, it's aligned with a hole, a hole at 1. So I really want to get this in. So a hole at 1. So there's my hole, right? Okay, that's f of x. Right? What we did was we traded f of x for a function that agrees with f of x everywhere except one point. Okay, we came up with this new function. Let's just call it g of x.
Oh, that's where that extra dot comes in.
Okay, g of x fills in the hole. G of x is a new function that's exactly the same as f of x, except it agrees at all but one point. It fills in the hole. What's the advantage of that? Well, the advantage is that now, because we filled in the hole, we can play the old trick of asking the ant, where do you think you're going to step? Where you actually will step, right? Because the hole is filled in on the red function, we can just say, well, what is the value of the function there? Because that's where the ant thinks he's going to step. Isn't that cool? That strategy is literally called in math, finding two functions that agree at all but one point. So when you do this, you are, now keep in mind, you got to realize this is a different function than that one was, isn't it? It really is.
But isn't it essentially equivalent, or shouldn't it be?
Well, it is, because it's different by 1 point, right? But in the original function, if I looked at the domain, x couldn't be 1, right? It can be 1 here. Isn't that cool? Wow, isn't it? Don't you just love calculus? Is so cool. I mean, you finally get to do like real stuff.
Better than geometry. Okay. All the pictures.